The GE90 engine, during test performance, crossed 127,000 pounds of thrust. A record it held for many years, only to be surpassed by its successor, the GE9X engine. But the engines commercially used, on the Boeing 777, are flat-rated to 115,000 pounds of thrust. So how is the rated thrust maintained, why is the engine power limited, and how the forward engine thrust gets reversed? Our final installment, of the Boeing 777 GE90 engine series, will explain everything related to the engine power. The thrust of the engine is controlled by the electronic engine control. Advancing the thrust lever to full forward position, the EEC increases the fuel flow in the combustion chamber, and drives up the engine speed, thereby increasing the airflow, to reach the engine's rated thrust. For the engine to maintain the rated thrust, it needs to maintain a constant mass flow rate. The mass flow rate depends on three factors: density, velocity, and area of cross-section. The total thrust of the engine is the addition of the thrust produced by the core airflow and the bypass airflow. On the GE90, the bypass airflow contributes 83% of the thrust, and the core airflow contributes the remaining 17%, which signifies why the turbofan engines are so successful. Burn the least possible fuel in the combustion chamber, to drive the massive aerodynamic fan, designed to accelerate larger quantity of airflow, which increases the efficiency for the given fuel burned. The EEC controls the thrust produced by the engine, by controlling the N1 shaft speed, and does not use the N2 shaft to control the engine thrust, as the N2 shaft only deals with the core airflow, that contributes a small part of the engine thrust. Whereas controlling the N1 shaft, gives control over both the core, and the bypass airflow, that is the full engine thrust. The EEC sets the engine N1 speed, depending on the outside air temperature. There are two sources of outside air temperature data to the EEC. The air temperature probe, on the inlet cowl of the engine, and the Air Data Inertial Reference Unit computer, which calculate outside air temperature data, using the temperature probe of the aircraft. The engine-rated thrust is generally determined in the standard atmospheric condition, where the outside air temperature is 15 degrees Celsius. But the engines installed on the aircraft will operate in changing environmental conditions. The air density decreases as the temperature of the atmosphere increases. This compromises the engine's ability to maintain the mass flow rate. Let's understand how the engine compensates for changing air density in different atmospheric conditions. In a low atmospheric temperature condition, the air density is relatively higher. If the engine runs at the standard speed, then the thrust produced will exceed beyond the rated thrust. Therefore, the EEC limits the N1 speed, to reduce the airflow, and ensures the engine maintains the rated thrust. In a high atmospheric temperature condition, the air density is relatively lower. If the engine runs at the standard speed, then it will fall short of the rated thrust. Therefore, the EEC increases the N1 speed, to increase the airflow, and ensures the rated thrust is maintained. If the temperature further increases, the EEC continues to increase the N1 speed, but only to a certain point. After which any further increase in the temperature, the EEC starts to reduce the N1 speed, and the engine thrust output decreases below the rated thrust. This is done to protect the engine. Running at higher speed in a hot climatic condition can drastically affect the service life of the engine. The GE90's maximum engine speed is much higher, and the engine is capable of producing thrust well beyond the rating. But to increase the service life by not pushing the engine to its maximum limit, and to ensure the engine has enough margin to produce the rated thrust in all possible climatic conditions, the engine is flat rated to a lower value. To achieve this, the EEC is fitted with a thrust rating plug. The rating plug programs the software in the EEC to limit the engine thrust to 115,000 pounds. The EEC software will now ensure the engine does not go beyond this rating. The same engine can be installed on the other types of the Boeing 777 aircraft by changing the rating plug that limits the maximum thrust. Now let's operate the engine thrust reverser. The forward and the reverse thrust lever have an interlock mechanism that prevents simultaneous operation. When one lever is in use, the other gets locked. Therefore, to use the reverse thrust lever, the forward thrust lever has to be moved to idle. The lever has two detent position, reverse idle and maximum reverse. The lever cannot be put ahead of the reverse idle position, until the reverser is completely deployed. Putting the lever to reverse idle position, sends signal to the EEC, to operate the engine thrust reverser. The EEC operates the thrust reverser, when the aircraft is on ground, the engine is running, and the forward thrust lever is at idle. Once all conditions are satisfactory, the EEC opens the reverser's hydraulic isolation valve. This sends hydraulic pressure to a direction control valve. The DCV controls the hydraulic pressure direction to the thrust reverser actuators. The engine thrust reverser is a combination of two halves, and each half has 3 actuators. The DCV applies pressure to the extend side of the 6 actuators. The actuators extend to move the reverser sleeve to the aft. Connected to the reverser sleeve are the blocker doors that gets dragged with the sleeve and moves to closed position. The engine bypass airflow that contributes majority of the forward thrust hits the blocker doors and vacates through the cascade segments. Cascade segments ensure the exit airflow is not turbulent. Sensors on the actuators send the reverser position data to the EEC. Once fully deployed, the amber indication turns green. The forward engine thrust has been reversed. Now the reverser power can be put to maximum by moving the lever further aft. The EEC increases the fuel flow in the combustion chamber to drive up the engine speed, and thereby increasing the bypass airflow that is now producing the reverse thrust. However, the entire engine thrust is not reversed. The core airflow continues to produce the forward engine thrust. Thrust reversers supplement the aircraft braking system in stopping the aircraft after landing, especially in wet runway conditions. To stow the reverser, the lever has to be moved to reverse idle. After the engine reaches the idle speed, to the stow position. The direction control valve changes the hydraulic pressure direction and retracts the actuators to move the reverser sleeve forward. The blocker doors open to allow the bypass air to flow through, and the engine switches back to producing the forward thrust. Once the reversers are stowed, the EEC closes the isolation valve to deactivate the system. Finally, let's shut down the engine. Moving the fuel control switch to cut off closes the fuel valve in the hydromechanical unit and stops the combustion. As the engine decelerates, the EEC starts to save all the parameters and fault data of the entire engine run. At 7% N2, the alternator power supply to the EEC is disconnected, and the EEC switches to the aircraft power supply. As the engine comes to a standstill, 5 minutes later the power supply to the EEC is disconnected. With that, we conclude the Boeing 777 GE90 engine series. Thanks for watching.